So the final step is to insert the series that we have. And our series, recall, is to say that P of R equals sum on n. It's an ordinary power series. N goes from 0 to infinity. Some set of coefficients, Pn times R to the n. Now, when I insert this series into my equation, right, you can see there's a certain set of terms that I'm going to need. So let's develop series for each of these different contributions. P over R, P prime on R, and P double prime. So the series for P over R is actually fairly straightforward. I just take this series and divide by R. So that will give me a sum. N goes from 0 to infinity. P sub n times R to the n minus 1. And I'll go through these quickly. They're pretty straightforward. The trick is going to be how we manipulate them. So P prime is sum. N goes from 0 to infinity. We know how to take the derivative of a sum. You take the derivative of the individual parts. P is a constant, so I take the derivative of this. N comes down, so I have n times Pn. And again, I lose 1 power of R when I take my derivative. Next in line, I need P prime over R. That's the next in complexity. This will be the same series as above, except of course now I have 1 fewer power of R, so I'm copying this down, and then it's R to the n minus 2. Next and final, I need the second derivative of P, so that will be P double prime has to equal sum n goes from 0 to infinity. I'm taking the derivative of P prime, so when I take the derivative I have these factors, but another factor, and n minus 1 comes down, multiplying what I had, and then R, of course, has 1 fewer power in the series. Terrific. Now, here's where a little bit of thinking needs to go in. The job now is to insert these, right, into my power series. And then what I hope to do is to collect into my equation. And what I hope to do is to collect term by term the different powers of R to finally make my final stage of analysis. And I can't quite do that though, because you'll notice the sums that I have really are not on an equal footing. These terms have a different exponent in R, so it's going to be hard to kind of pick out all the terms that have R to a given power, like the R to the 7th term. So the way we do that, I like to think of this maybe as power series management, is we want to rearrange these sums and rewrite them in a special way. So let me show you how this is done. And this is the one subtle part of the algebra involved. I would really like this n minus 2 to match n minus 1. So to allow that to happen, I'm going to change my summation variables. It's very much like changing your integration variable. To be very specific, I want to pick a new variable. It's going to be the new n, which I will call n prime. And I want it to be so that this new n prime minus 1, right, will look just like the old original n minus 2. If I do that, then my new sums and my new variables will also have R to the n minus 1 powers, and things will line up nicely. Now that's what I want. That tells me then that n prime will actually equal my new variable. If I move the minus 1 to the other side, it's actually equal to n minus 1. Or the other way of thinking about this is that the old n that I had, right, is going to now be replaced by my new n, my n prime, plus 1. So let's work through then the consequences of this for my original sum, for this sum here. So if I look at this, I'm going to be summing now on all n prime. Now the original n runs from 0 to infinity. The new n is n minus 1. So this actually has to run from minus 1 up to infinity minus 1. But of course that's silly. Infinity minus 1. That's just going to infinity. The terms within the sum, the old n is now replaced by n prime plus 1. So I will have n prime plus 1 times Pn prime plus 1, and then times R. N becomes n prime plus 1 minus the 2 will give me the nice n prime minus 1 that I was shooting for. So that was a little subtle, but I think if you think it through carefully, you'll see that actually is the appropriate thing to do. Now, This is looking good. We've got the, apart from the fact we have a dummy summation index n prime instead of n, this series does look just like the other two series I want to combine it with. The slight problem I have, aside from the name of my variable, is that this sum, though, starts not at 0 like the others, but it starts at -1. And here nature is a little kind to us, because if we think about that term, the term when n prime equals -1, you will notice that this factor actually ensures that I get 0 for that first term. So even though technically I need to include it, it's 0. So if I ignore the first term in this sum, I do not change the validity of my result at all. So I can actually say I'm not going to start off from -1, but I'm actually going to start off from 0. So n prime will run from 0. And the final thing, of course, that I can do now is I don't need my dummy summation index anymore because I've carried through my analysis. I know this is now a valid sum. I can call my dummy summation index anything I like, and I'd rather call it n. So at this point, if you like, you can just scribble out the primes, and we have a nice valid equation. The second term I can handle with precisely the same logic. So let's go through this one more quickly. This is a sum, right? N prime has to start from -1 just like before, and it will go up to infinity. My n now again is replaced by n prime plus 1. So the first term actually becomes just an n prime. So I'll have n prime. The next term becomes n prime plus 1. The next term after that is p sub n prime plus 1. And my exponent then is r to the n prime plus 1 minus 2 is n prime minus 1. Next thing to observe, again, I've got this extra term, but once again, nature is kind. The first term, the n equals -1 term, actually is guaranteed to give me 0 because of this factor. So I can, without any changing of the validity, I can just run my sum as I would like as the other sums run on the same footing from n equals 0. And finally, once again, n prime is just a dummy summation variable. So now that I'm done with the hard part of my thinking, let me get rid of those primes and change my variable back to n. And I have a nice series then that I am ready to insert into my differential equation.